Okay, so Isotope, you recently, I think you sponsored a publication by STL Partners, a report. The title is Sustainability Insights, Navigating Sustainable Edge Strategies. And I believe the focus is particularly on the telco industry. It'd just be
Yeah,
good, I guess, to understand what the particular headline findings were of the report.
sure. Yeah, well, there were a number of findings. It was a pretty comprehensive report. Some of the big ones was by adopting some sustainability strategies, we found that telco providers can cut their energy usage by 3 to 5%, which is the equivalent of 1 million tons of carbon dioxide that are emitted into the atmosphere every year. So this can have a significant amount of savings, both in terms of environmental impact as well as operating cost. For the average large size telco, that 5% reduction in energy could turn into $40 million of savings a year just in energy bills. So it has a massive potential immediate impact on the bottom line as well as on sustainability efforts. And as we're also seeing that the edge and telco markets, were around a $9 billion market size in 2020, and it's expected to grow at a 49% CAGR over the next 10 years. So that's a $450 billion market, by the time we get to 2030. And if we extend that into the amount of energy consumed as a result of that growth, you're just going to continue to see more and more energy consumption. And and what we're seeing then also is that 73% of the energy consumption for telcos comes from the radio access network, from the RAN network. And if we can materially reduce the amount of energy that the RAN consumes as we move from the current ecosystem into vRAN and O-RAN, that could be a material reduction as well. And then finally, when we get back to the core of the network, today data centers are consuming about 1.5% of the energy on the planet, and we're only expecting to see that grow as well. So if we can become something more responsible about how we utilize energy, and the way that we do that is we change the wasted energy within all of these ecosystems. And the number one waste of energy, of course, is on cooling. And so if we can use every electron possible for compute instead of cooling, that obviously creates more efficiencies, cost reductions, and more sustainability.
Yeah, and I mean, obviously, sustainability, big issue for the data center industry, and they're already making significant sort of progress and got a roadmap. But I'm wondering, at the moment, has it been the major focus on the bigger facilities, the standard, whereas the edge? And I mean, I'm not saying the edge is being neglected, but is it partly for the reason you've explained that at the moment, obviously, it's a significant piece of infrastructure and for the data center, but the growth is going to be significant. So at the moment, it's perhaps been overlooked a little bit just because it's not as big a problem, if you like, as all the big data centers that everyone's very aware of.
That's right. I think the neglect of the edge has been for multiple reasons. One, the core obviously is the biggest consumer potentially of energy in the past. But as we continue to need to move more compute closer to the consumer, closer to the edge, you're going to see power-hungry chips, AI chips, further and further away from the core of the data center. So that obviously is going to drive one element. The second element is that the edge is, especially for telco, has been a fixed device, right? It's been a purpose-built device, and there's really nothing you can do to change that. But as we're moving away from these purpose-built devices into the virtual RAN and eventually into Open RAN, where software will do more of the heavy lifting and the hardware becomes more commoditized, that opens up the opportunity then for alternative ways of looking at that hardware, looking at how that hardware operates and how we cool that hardware. So I think the opportunity to consider how we operate at the edge is changing now as we're moving away from proprietary hardware towards more off-the-shelf hardware.
And in terms of the types of infrastructure required for particularly with sustainability in mind for the edge compared to what we call mainstream data centers, I mean, are they particular challenges for the edge in terms of ensuring the same kind of sustainability roadmap as there is for say larger data centers, centralized data center, or is it just more of the same, but just being used in a different location?
Yeah, well, obviously the environmental factors are the biggest difference between edge and data center. When you have everything sitting in the same big, large facility, you can control that environment much more in terms of its cleanliness, what's in the air, what's interacting with the compute. As you move to the edge, whether that be, at the base of a tower or at the top of an office building in a dense urban environment or wherever it is that you're trying to deploy or in a factory, all of those things are going to create environmental conditions that are much harder to control. And so the more you can insulate yourself from those conditions, the more efficient you're going to become at the edge. And so that's where, as we have traditionally tried to spin fans, blow air over the compute elements in order to eliminate that heat, the more the heat, humidity, dust, particulate, everything that's floating around in the air becomes a factor. The more we can shield the compute from those factors, obviously, then the more we can become efficient at the edge. And that's really going to be the number one difference maker between what's happening in the core and what's happening in the edge.
And in terms of the specialized or different infrastructure, if you like, that's required for the edge and to do what you said, I mean, is there a whole range of solutions, or are we mainly looking, as you alluded to earlier, specialist cooling? That's the big win, but are there any other bits that need to be considered as well?
Yeah, I think the best edge deployments are going to be the ones that obviously lower energy costs by, again, moving every electron away from ancillary performance elements like cooling towards compute. So, as you get to the edge, there are plenty of places, especially on the extreme edge, where you simply have a limit to the amount of power you can pull into that facility or to that compute node. And so you want as much of that energy used for productive elements, not for ancillary things like cooling. The second thing that you got to also think about on the edge is the maintenance costs. It can be very expensive to send a technician either out into the extreme edge somewhere where they have to drive quite a distance, or trying to get access into office buildings or other places where you may have deployed a radio antenna in a closet somewhere in someone's office building. So it can be very expensive and time consuming. So you want to lower your maintenance costs as much as possible. And that means creating devices that are going to be hardened enough that they don't break down as often as perhaps traditional compute has broken down. So I think those are the biggest elements that are a good fit for edge.
And in terms of the specialist cooling, and we're talking, I guess, here about liquid cooling. I think the report, and don't ask me to remember all five, but hopefully, I think it mentions 5 different types of liquid cooling. So perhaps you can just refresh or outline those 5, but also the conclusions the report came to as to which ones of those, or which one might be the most potentially the most effective when it comes to sustainability at the edge.
Yeah, so there are many ways to reject heat. Obviously, air has been the one we've used the most often, and it's the least efficient. And then there are ways to capture heat using liquid. The oldest technology is basically looking at the very hottest components within a compute environment, which are generally the CPU and the GPU, and to place over them a heat sink that has a water loop attached to it. And the water flows across that heat sink, and the water is able to capture that heat and move it. But what you end up with is a hybridized environment. We call that direct to chip or cold plate environments, and it's effective at removing the heat from those hottest components. But the rest of the ecosystem is still being cooled by fans, and so you've got both fans moving across the motherboard and the memory DIMMs and the power supplies and that part of the environment, and then the water loop is moving across the CPUs and GPUs. And again, it's kind of like a hybrid car at that point. You have both a gas engine and an electric engine at the same time. So it moves you towards where you want to go, but it doesn't quite get you all the way there. You have double the maintenance then potentially, and you also, of course, have water entering into your ecosystem. So you know, water that may drip and leak can cause catastrophic failure within any sort of IT environment. So that's always a risk that you take with that environment. A second one that's been around for quite some time is the idea of using a dielectric fluid, which is a non-conductive fluid, usually some sort of byproduct of a petrochemical. And to do that, you simply build some sort of container, a tub, a tank, and you submerge the IT in that, and you swirl the liquid around. And again, that's can be effective, more effective than air at capturing, but it creates a number of challenges. Most importantly, in terms of its effectiveness in capturing it, you end up creating thermal plumes coming off of the hottest things that do similar things to air, which is you can get one hot thing, and then the hot oil or dielectric fluid is now moving across some other thing, so it moves heat from one element in the compute to the other. And then, of course, maintenance is a nightmare challenge, because now you've got to somehow extract the IT from this tub of oil and let it drain, and of course, at the edge, that becomes really challenging, because now all the ecosystem, the environmental things that are floating in the air are now getting inside of your tub of oil. So it becomes a challenge. And then, you know, you can also utilize a different type of fluid, which is called a two-phase. And what that implies is a fluid that has a very low boiling point. And what that means is, as it is exposed to the heat coming off the compute, it turns into a vapor, from a liquid, and then you allow that vapor to come in contact with a cold plate outside of the IT, and then it rejects the heat that way and turns back into a fluid, and that can be hyper efficient. Unfortunately, though, those fluids are quite harmful to the environment. They have, they're the best ones on the market are 9 times worse, 10 times worse than carbon dioxide for the environment. So the EU has already sued the largest manufacturer of that type of fluid, and they've decided to no longer produce that fluid, and had to pay a $10 billion fine to Belgium as a result of it. So that part of the market just doesn't seem sustainable, not to mention the fact that you as an operator within that environment also are breathing that fluid in as it vaporizes around you, so it can become harmful to people too. So probably not the best solution for the environment and for the people around it. So what we have developed is what's called a precision liquid cool type of environment, and what that implies is using that single phase, so the type of fluid that is completely non-toxic and harmless to the environment and doesn't turn into a vapor, and utilizing a similar type of system like cold plate, where we're putting the coldest possible fluid to every component within the environment. So not just the CPUs and the GPUs, but every component is getting the coldest fluid directly: the power supply, the memory DIMMs, the SSDs, the GPUs, the CPUs. Everything gets just the minimal but exact amount of fluid it needs in order to reject the heat. And then it simply creates a small, very small centimeter and a half amount of fluid on the bottom of the chassis, which is then pulled back to the rear of the chassis, and the heat is rejected that way. And we can capture then nearly 100% of the heat in that environment, and in a completely sealed environment. And that's why that's so important at the edge, is that now you can have a completely sealed environment in which the heat is being rejected in a much more passive way. You don't need fans. And that's how you can then massively reduce your energy consumption, up to 40% within a data center environment, and 20% at the edge. So these are material reductions. And that also then leads to a 30% reduction in maintenance costs, because we're eliminating the number one thing that fails in servers, which are fans. But we're also then protecting the environment from that dust and particulate and other things that get sucked into it normally. And that's what causes failures oftentimes within the ecosystem. And then by reducing vibration and heat fluctuations, that also helps to maintain the components for a longer life cycle. They don't unseat themselves because of the micro vibrations of a fan, and they don't that nanometer of fluctuation when it goes hot and cold and hot and cold and hot and cold over time can cause components to fail. So that's a long answer to give you all five of of those various environments, but the STL report shows that that the best environment for the ecosystem of telco and edge, both at the core data center but also in the edge, is a precision liquid cooled environment, because you can again achieve that energy savings, reduce those energy costs, and ensure optimal performance and the maximum sustainability.
And I'm just wondering, I mean, clearly in the larger data centers, the opportunity to reuse the waste heat, I guess, is there.
Mm-hmm.
But at an edge facility, is there enough, if you like, waste heat to be useful to repurpose? I mean, as you say, if there's something at the top of an office building, it would seem obvious to maybe capture that heat to use it in the building, or is it just not sufficient quantities of waste heat to be useful?
Yeah, I would say probably for most base unit, like at the base of a tower unit, there probably isn't enough heat that you would put the ecosystem in to capture it, because you're generally only operating a small rack of servers, so it's relatively low amounts of heat. But you certainly could. It's quite simple to do by simply putting a piping mechanism that captures the heat and routing that piping to wherever you want that heat to go. So it certainly can create a sustainability loop there. And certainly in certain environments, colder environments where that is important, or in environmentally sensitive areas like the EU that are working very hard to capture as much of that heat as possible and reuse it. Yeah, that could be a powerful tool for any operator.
And you outlined in the previous answer the benefits of this approach. And I'm just wondering, in terms of the telcos, the opportunity are just, I mean, anecdotally, or I don't know if the report revealed it, is the industry fully switched on to this opportunity at the moment, or is there a period of education required? Because they've, as you say, they explained they've been doing things in a certain way. They know they have to change, but they haven't maybe understood fully, the opportunity that change provides them, as opposed to just doing it because they have to do it. Just your thoughts as to where the telcos are, I guess.
Yeah, I'd say the last 2 years have been really an educational time period. And in my conversations with many of the major telcos around the planet, they're doing their best to understand what the move towards vRAN and ORAN is going to do for their ecosystem, as well as thinking about that sustainability and lower operational costs within the core data center. So I'd say 2024 is going to start to be an inflection point in which the telcos are moving away from experimentation into deployment. And so we're going to see, I think, probably mid to late this year, more telcos moving towards some alternative cooling technologies, both at the edge and in the core data center. And that's obviously not something that just happens all at once. It's going to be part of their refresh cycle. It's going to be part of a hybridized environment. And that's the important part then, is that you if you're a telco operator, you want a technology that allows you to operate both at the same time. And that's again the advantage of a rack-based precision liquid cooling, is that you can be running a precision liquid cooled rack next to an air cooled rack at the same time. So, or even within the same rack, you can have those operating simultaneously, and that allows you then to transition from one technology to the next technology. You don't have to do a full rip and replace, which is very costly from a CapEx perspective and doesn't necessarily make sense. You don't want to take down a whole facility and rebuild it. You want to be able to do it in small amounts. So I think having that lower barrier to entry to new technologies is also going to accelerate the movement within the industry. And we're going to see a lot of that at MWC this year, I think.
Yeah, that was going to be my final question, because I know what you're discussing there. Part of the excitement is that I believe yourselves, Iceotope, you've got a solution that you're going to be introducing to the world at MWC in the near future. And I suspect you can't tell me too much, but if you can give me a flavor of what people might expect when they turn up at MWC next week, it'd be good, as much information as you're allowed to share.
Sure. No, I'd be happy to tell you now. It's what the big launch is going to be is what we call our Cool RAN. And obviously the name implying that it has a specific use case towards the radio access network at the edge for telcos. And we're using that based on a partnership with Intel and HPE on their DL110, which is their short depth telco and edge based server. And what we're able to do is using the fourth generation Intel scalable processors, we can create an environment again, a sealed environment that is deployable in a completely passive way. That is, that you don't require any ecosystem around it. You don't need air conditioning. You don't need a water loop. You don't need any sort of environment in order to deploy this into any facility, whether that be in an urban dense environment or an extreme edge environment. And it's designed then to be able to go into whatever type of rack or facility that you need, because the chassis itself is an IP67 rated NEB certified device. It allows you then to passively reject heat. That is, again, the heat that is being created by the compute is going to be passively rejected into the air. You don't need to worry about the ambient temperature around it, and it can operate in these extreme environments from negative 40 degrees Celsius all the way up to 55 degrees Celsius. So whether that be the harshest environments near the poles or the hottest environments near the equator, all of those are in scope for this device. And so we're excited to be able to showcase that device at multiple booths at MWC next week, and continuing that partnership then with HP and Intel. We'll also be able to show our core data center device, which we call Cool 2, which is based on the HPE DL380 Gen 11, which is more of a mainstream server. And that is a fully, rack mounted data center type of an environment, which can also be used on the edge if you want that kind of heavy GPU loaded AI as close to the data source as possible. So we're going to have a number of different ways to show that we can create a fully sustainable, scalable, and serviceable ecosystem for telcos to be able to deploy.
Okay, that sounds fascinating. So, I mean, some great insights into the report and the technology that people are going to see next week. But at least for now, Nathan, really enjoyed the chat, and thank you very much indeed. Thank you.
Bill, it was a pleasure. Look forward to talking to you soon.
Thanks again.